Now, so far we've seen how we can take data, take observations and features of an observation, pass it through a neural network, and get a prediction, right? And we saw that, if we start with something like x equals 3 and 1 to represent our cell area and number of concavities, that then we then take this feature vector, dot it with our weight vector, add our bias term, and get an output somewhere between negative infinity and positive infinity. We then take this output, right, this value z, and pass it into our sigmoid function, right? And that's really the linear layers of a single neuron. And we saw this, just to show you, one thing you'll see is that you can summarize these two layers in a single line. So what I mean is, right, this is just like our linear layer, w dot x plus b. And then that gives us an output, and we pass that output to our sigmoid function. This x of I, that's just representing the fact that this is a single observation here, all right? This is still a vector, but represents a single observation. And you can imagine that really, like, ultimately we'll have multiple, maybe we'll call this like x of 1 and x of 2. But in each case, what we'll do is still pass that vector to this function. Dot it with w, add the bias, take that output, pass it to the sigmoid function. And then what we saw, so this is what we saw by hand, and then when we translated this to PyTorch, we saw effectively it's the same thing, right? Linear layer followed by a sigmoid layer. Here we're specifying the number of features that we want, and that just or the number of, the length of our weight vector, I should say, and that matches the number of features. So here we'll have a weight vector of 2. We're doing a single neuron. We dot the weight vector with our features, add b, pass this output to the sigmoid function. And you can see that's what I'm doing here. Taking a feature vector, passing it to my neural network, and that's just going to pass it through these layers until we get a value between 0 and 1. Now the issue with this is that, this prediction isn't any good. And the reason why it's not any good is because these parameters, the weights and the bias terms, are random. And if we, here I'm selecting that first layer, and you can see if I just recreate a neural network, they're different each time. And because these weights and bias terms are different each time, when we then dot those weights and biases, or dot the weight and then add the bias with this vector, we're going to get a different prediction each time, right? You can see that this prediction changes each time, which kind of proves to you it's not very good. It's just produced randomly. So what we want to do in this lesson is train our neural network, is teach our neural network what are the proper weights and bias terms to make a prediction that actually, corresponds, like does a good job of predicting if these cells are cancerous or not. Sounds like a noble goal to me. Okay, so what I'm doing here is I'm actually loading up data. And if you go to the lessons here, don't worry, that data still is right there. So you'll be able to load up the data as well. And this has a lot of data. It has like 570 or 69 rows. You see here, the 0 is indicating that this is not cancerous. So one thing interesting that we can see is like this is how our neural network is going to learn, is we're going to feed it actual examples, like past examples, where it knows the answer. It knows, okay, here was the mean area, and it wasn't cancerous. And here was the next area of the cells, and it, again, was not cancerous. And again, not cancerous, but sometimes it was, okay? And just one point of clarification, it's mean area right here, because really the way this data set works is it's taking the average area of cells in a picture, right? So you can imagine they're like photos, and the TAs, the graduate students, are writing down the average area of those cells, and then also saying, and I observe that this cell is not cancerous. And then we want to feed this data set to our neural network so that it learns, okay, if I take this mean area, multiply it by a weight, W1, that's going to be my Z. Maybe there's a bias there too. That's going to be my prediction, or sorry, the output of my linear layer, and then we're going to pass that to the sigmoid function. Okay? Cool. So our goal now is going to learn, right, this W1 value so we actually get good predictions that line up to what, these graduate students observed. And that way, if we do a good job of predicting this data where we know the answers, we know, okay, this was not cancerous, but this one was, and we have a weight that properly produces the right output. Hopefully it's close to 0 in all these cases and close to 1 in this case. Well, then we think like with future data, it would also do a good job. So that's the idea. We want to learn this weight. The reason why I'm saying just, this weight is because, and not the bias, is because we're going to simplify our function, right? Because learning 2 parameters is harder than learning 1. So let's just keep a simple hypothesis function where we're just going to take the mean area, multiply it by a weight, get a value from the linear layer, and then pass that value to our sigmoid function to give us a number between 0 and 1. All right. So the next question is, okay, well, how do we learn that weight? So here you can see, this is our linear layer, and we pass this output to our hypothesis function. And here I just define this in code. We actually don't need this at all. We have our linear function, our linear layer, do W1 times by the mean area, pass that to my sigmoid function. Cool. So we'll start by seeing if we can do a good job of predicting just a single observation. So can we find a weight that just produces a single observation? And then we'll worry about finding a weight that all in all does a good job on the entire data set. So for now, we'll just worry about one observation. And the way that we'll do this is our first area. This is our first weight. We're just choosing a random value. It could be like anything, but we'll choose 1. And this is our target. Our target is 0. This was the actual answer, right? Was that it was not cancerous. And then what do we do next? Well, we'll pass through the weight and the target. We'll see how, what is the output here. Let's print out Z, I guess. And then we'll pass this to our sigma function to make a prediction. Now let's just take a look at the prediction. Okay, so we got, is that right? Okay, yeah, so we're printing out 1.001. That makes sense. Let's change the weight maybe. Okay. So we're printing out the Z value is 2, and then we compress that down using our sigma function, so we get a prediction of 0.8810. Let's comment this out so you can see it. This is our prediction, 0.8810. I'm going to copy it here. And the actual value was actually 0. All right? So this was the actual value. So, what we could do is we could just try different values here and, find a weight that does a better and better job, right? It seems like 4 is close. Oh, no, 4 is doing a worse job because it's 0. So now we have, let's move this to maybe -4 or something. And now that seems pretty close. All right. So, okay. So we have this 0.0179. And that's pretty close to 0, and I guess that's pretty good. But really what we want to do is we want to have a more formal way of evaluating how good is this prediction, okay? And the way we'll do that is by defining something called error. Error. So error is how far off is our prediction. And if you think about it, we probably want this error to be low. So the formula for error is actual minus expected, okay? So the actual value here is 0, and the expected or predicted value equals here 0.0179 when our weight is -4. Okay? And then if we calculate it, it breaks. Expected is not defined. Yeah, let's call this predicted, I suppose. All right, so we get -0.179. let's use some different values. I want to illustrate a point. Let's say the actual value is 1, and we predict 0.5. All right, now our error is 0.5. Okay, so this is for a single observation. For a single observation. Now imagine that we have our next observation. Our actual this time is 0, and our predicted is again 0.5. Let's just imagine. And now we have our next error. We get this. Notice that if this actually produces like a problem for me, because if I want to say like what is the total error across both observations, well then it makes sense to me, or one simple solution could be just to add these up, right? But if I add up 0.5 plus negative 0.5, well that gives me 0. And in other words, it's kind of saying, oh, well, yeah, the total error is 0, which is not right. You know, it sounds, you know, like that sounds great. The total error, we're not off at all. But really, we were off. So instead of using error where these values can cancel each other out, what we do is we use squared error. Okay, so with squared error, all you do is you take actual minus the predicted and you square it. And that's called our squared error. And now this time, we get 0.5 times by 0.5, right? Because the error was 0.5, so error times by error, and that gives us 0.25. And even when we have a negative error, or negative output here, when we move to squared error, we should do a little better, right? Because now this also gives us 0.25. So this time we don't have that problem of our errors canceling each other out. Rather, we can see that, you know, each one is off by 0.25. And we say total error is, okay, we're off by 0.5. Total squared error. Let's call this like sum of squared error, right? Because we're adding up each squared error here. We'll see that some more. So that's the formula that we're going to use, right? We said we want to kind of get good, right? We want to turn this, how far off are we, into an actual formula. And the formula we'll use is actual minus expected, okay? So that's what I'm doing down here, right? This is the squared error formula. Actual minus the predicted squared. All right. So just to go through the whole procedure now that we've done this, we start with an observation, we start with a random weight, and we kind of know the answer, right? This is what the nurses, the graduate students actually observed, that there was, let's say, cancer in this example. Actually, they observed there was not, so we'll change it. Then we take this feature and the weight, and we pass it through to the linear function, and then we get an output z, and we pass this to the sigma function to make a prediction. So this is now our prediction, and the next step is to evaluate, well, how good is that prediction? And to do that, we say, okay, well, here's the first target. Here's the actual value. Let's call this, I guess, actual. Minus what we predicted, and then we square it. And that is our squared error. Okay? So this is how good of a job we did. Now, this is just for one observation. So what we want to do next, right, is then do this across all observations. Calculate the squared error for each observation at this weight. Add them up. Add up all those squared errors. And then we can see maybe how good a job this our neuron does when we are using this weight of 1. Okay? Right? Because we want to see how good a job is this weight across all observations and making predictions. Cool. So let's move on. Let's do that. So here's our areas. I'll show you how we do that. Here's our areas and here's our target, right? These are the mean areas across all of our observations and the actual answers across all of those observations. So the areas look like this and the targets look like this, okay? And now we can kind of apply that same procedure to all of our data. To do that, you can see what I'm doing. I'm zipping together the areas and the targets, okay? And then what I'll do is I'm going to loop through for each observation. I call this my paired data. I'm going to say for each feature and target in the paired data for each observation, we're unpacking the feature and target, and we're going to pass that feature into the linear function, so like 1.001 into the linear function, get the prediction, right? Get the output, and then calculate the squared error, right? Say, okay, this is what we predicted, this is what was actually observed, and this is the squared error. So we do this for each of these and then add them up. So for each observation, calculate the squared error and then add them up. And if we do that, we get a value, I guess here, of 164.85. Now, I think the main question we all have is like, okay, what is the point of this? And the point of this is that, well, we have a way of summarizing how good a job this weight does, okay? And really, what's even more valuable is we can now maybe try different weights. So if I set, let's try this to be 187. That seems to be worse. Let's try the other direction. Let's do like -1. That seems to be better, okay? So we can maybe do trial and error of our weights. Try this on our data, right? On our data set. Calculate the sum of the squared errors. And we want to effectively choose the weight that produces the lowest sum of squared errors. So how do we do that? Like we said, we're just going to try a bunch of different weights. So that's what I'm doing here. I'm creating, numbers from -2 to +2 or close to it. And then we'll loop through, try each of these weights, and see what the sum of squared errors is. So I'll just show you. I guess that's what I'm doing here. I'm saying for each weight in this list of weights, calculate the sum of the squared errors on my data set. And then show me. So here are the squared errors. And then here are the weights. Right? Here's those weights that we were trying out. Okay? So in other words, when we did -2, we got 187. We did -1.8, we got 179. And this actually becomes a little, it's really nice to plot this. So we'll plot these different weights as our x values and the output of using these weights, right? The cost or the sum of the squared errors of using these weights as the y value. So you see that here's the weights, there's my x value, here's the squared errors, my y value. Let's plot them. And this is pretty common, that we get a curve that looks something like this. And what weight is best? Well, it's the weight that produces the lowest error. So if this is a pretty high error, and this is a fairly high error, the lowest error seems like is right here. Yeah, 140, okay? But the real importance is we should be using a weight of -0.2 for our parameter, right? For our parameter. And just to show you that that's really works, I tried this another way using sklearn, and here I'm passing through that same data set of the areas and the answers, right, the targets, and the weight that does a good job of predicting those targets is -0.26, which is basically what we got, right? Okay, so that's it, right? Or we're going to learn a little bit more, but that's the first step, is how does a neural network learn the correct weight to use, the correct parameter? Trial and error. Start with a random value, define what we call a cost function, which in this case is the sum of squared errors, and find the value that minimizes the cost on our data set. And if we do a good job on our past data, where we knew the answers, and we had someone tell us whether or not something was cancerous, and we now found a parameter that does a pretty good job, or as good as we can, of predicting those actual results, then we think this parameter will do a pretty good job with future data as well. All right, so we saw how to train a neuron, but we're going to go a little bit deeper with that in the next lesson.